So my name is Alex Leader. I'm a postdoctoral fellow at UC Berkeley, working on a wide variety of projects, mostly aiming to try to detect this mysterious substance called dark matter. But I am, in a broader sense, an instrument builder. So I'm someone who attempts to build a lot of the instruments or to characterize how we can build better detectors to detect any variety of phenomenon out in the universe. And so I'm particle physicist, so I try to build detectors to find particles, but I'm also an astronomer because what I look for is dark matter, and dark matter exists everywhere in the universe, and we have lots of evidence from all over the place of what dark matter is in the universe, but we have yet to detect it here on Earth. So my job is to try to build something that can detect it here on Earth.
How did dark matter become a thing?
Dark matter has always been a mystery, and depending on exactly who you ask, it may have been discovered earlier or later, but it's generally accepted that it was first confirmed to have been not seen, if you will, in the 30s and 40s. And what the evidence for this was that a lot of very talented astronomers started looking at galaxies and looking at other galaxies, and specifically looking at the stars that inhabit these other galaxies. And just like the planets in the solar system, these stars will orbit around the center of their galaxy. And if you do long observations and you observe for a long period of time, you can then measure the speed of each one of these individual stars, just like you can measure the speed of the planets in our solar system if you look at them long enough. And by looking at the speed of these other stars and other galaxies, you can calculate how much mass is pulling on them, or how much mass is pulling on them. And what was mysterious was the fact that when they calculated how much mass was pulling on each one of these stars, there was a discrepancy between the number, the total mass that was calculated, and the total mass of all the stars that were visible in that galaxy. And so they were saying, well, there's got to be more stuff pulling on these stars than what we can see, and this extra stuff then eventually became what we call dark matter today, because it wasn't visible, it wasn't emitting light, but it was still pulling on all the stars in the galaxy. We see the imprint of this mysterious dark matter on a lot of these signals that come from the early universe. So if you imagine in the early universe, you just have a big nebulous gas of hydrogen and maybe some helium or what have you. And you have this gas just filling the void of the universe. There's nothing necessarily that's going to force that gas to start coming together. It's just going to kind of float around in the early universe and not really do anything. Where dark matter comes in is if there are little nuggets of heaviness. Let's say like there's a little clump of gas that's a little heavier than the surrounding region. Eventually, you're going to have gas start clumping or gravitating, moving towards that heavier clump. And what dark matter helps you with is you have something that now fills the entire universe, or can create pockets of heaviness and create like little magnets that starts pulling gas together. And eventually, once you start pulling enough gas together, at very, very large structures, you create galaxies, and on a much smaller scale, you actually create stars. And so the dark matter is something that helps create what we call structure formation, and it actually creates the distribution of the universe that we see today. So if there was no dark matter, everything would have stayed kind of nebulous and distant and just like a gas that would have filled the room. It would have been very difficult for it to actually form stars and galaxies and planets even that we're on right now. And it's called dark matter because we know it doesn't emit light, but we know it interacts with gravity, and so it attracts other objects to it, but it doesn't seem to emit any sort of signal that we've been able to detect. If we were to have a clump of dark matter, it would eventually like fall into the orbit of, say, Earth. But we don't know anything else about it. We don't know, would it emit a signal? Is it going to emit like a radio signal? Is it going to emit a electromagnetic signal? Is it going to interact with some other particle nearby? We don't know a lot of these questions, and so that that's still an open question that we have yet to answer.
How are you going to find out?
By building these detectors. And so I work on many different experiments simultaneously, maybe too many. And each experiment is designed to look for this dark matter particle in a different region of mass and space. So there are some experiments that they're called cavity-based experiments. And so they look like a big cylindrical tube. And we have to cool them to extremely cold temperatures, and we have to put them in strong magnetic fields in order to try to create an environment where the dark matter will want to convert from its invisible self into something that's visible. And so that's one style of experiment that we're looking at, called cavity-based experiments. Then there are other experiments that I'm working on that say, we don't need cavities. Cavities are complicated. Cavities are extremely difficult. And so they're building an antenna, and the experiment's called DM radio. And the antenna part of the experiment is just like if you've ever tuned your radio in your car, you change the frequency at which you're looking for a radio station. And so you can have multiple radio stations that you're looking for. And if you manage to tune your radio to the right frequency, suddenly you'll have sound coming out of your speakers. And so DM radio is trying, in a similar vein, to create an experiment that you can tune it similar to a car radio by changing certain parameters in your experiment. And the idea is eventually, as you scan through all these different frequencies, maybe one day you'll have some sound coming out of your speakers like an axion, converting into a visible signal.
Tell me one thing that you love about your job.
Another alternative answer I can give you is because I work with extremely cold things, so all my detectors, all my work pertains to instruments that operate near absolute zero, which is the coldest temperature possible. Like we're always just a hair breadth above the absolute coldest temperature in the universe. And this means that we work with a lot of very cold things, including the substance called liquid nitrogen, which is, when it's liquid, it's about minus 200 degrees Celsius. So it's way colder than anything you can experience in the world. And that has important applications for us. But it also has an interesting perk that I have made several gallons of liquid nitrogen ice cream. So over my grad school and into my postdoc a little bit, I use these extremely cold liquids to make ice cream flavor, like any ice cream flavor that you want. And so I've made, several gallons of things like key lime pie flavored liquid nitrogen ice cream. We made root beer flavored ice cream once. That didn't quite work out. We've also made, vanilla is kind of the standard. But yeah, what's nice about liquid nitrogen ice cream is you can use all sorts of crazy flavors, and you're not limited by the temperature of your freezer. So you can use some really, really fun ingredients.
Can I might get one?
I mean, if you can find me liquid nitrogen and cream and whatever flavor you want, sure, I could make some. But I don't know if we'll have access to that just on the fly here today.
Yeah.